Alright guys, so in today's video what we're going to do is start to make some connections between estimating our areas using Riemann sums and trapezoidal rule and being able to get exact answers. So the big idea of the first part of today's video is that if we add together enough rectangles, we get an exact answer. We saw this in our Desmos activity where we increased the number of subintervals, and the more subintervals and rectangles we made, the better our estimate got. So when I say if we add together enough, exactly how many is enough? Well, the answer to that is infinity. So in order to represent that we're adding together infinity rectangles, we use something called summation notation. This big cap, it looks like a capital E, is actually a sigma in Greek letters, and it means sum. So in other words, we're adding together a bunch of stuff. How much of that stuff? Well, we're adding together infinity number of rectangles. In this notation, the n represents how many of these things you're adding. Since we're letting the limit as n approaches infinity take over this problem, we're adding up infinity rectangles. Now, what exactly are we adding? Well, every rectangle is going to be made up of two things, a base and a height. In this problem, the height of the rectangle is represented by f of x because f of x is the y value. And so that's going to be the height of our rectangle. And delta x is going to be the base of our rectangle. It's the change in x, or the width of the rectangle that we're using. Just like when we do these problems with rectangles, we need a beginning and an end of our interval. So this is the x at the beginning, and this is the x at the end of the rectangle, or the area that we're trying to find. If we were to add up infinity of these rectangles, it would translate to computing an exact integral. So when we learned integral notation, we said it looks like this, which is basically a capital letter S for sigma or for sum. So these things are connected. Saying this, taking infinity rectangles, is equivalent to doing an integral. And just like this notation has certain pieces in it, an integral notation has certain pieces. Instead of writing the interval at the end, we write the interval on the integral symbol. We still put f of x inside of our integral, but instead of a delta x to represent the base, we write a dx because dx is just infinitely small. So basically we're making really skinny rectangles. Saying this and saying this are equivalent. So one of the things we need to know how to do is to take a summation notation and rewrite it as an integral. For example, if I give you this summation notation on this interval, can you rewrite that as an integral? So here's what you would do. You would write your integral symbol, and you would use the interval to fill in the bounds of the integral symbol. Now inside of your integral, you need a function. So you're going to get the function by looking here. In this notation, instead of using x's, we use m sub k's or c sub k's because what we do is we say, like, this is the midpoint of the first rectangle. This is the midpoint of the second rectangle. We're adding up a certain number of them, so we have to represent it without an x. But when we write an integral, we are able to just use an x. So all of these m sub k's are going to become x's in our new notation. So we're going to have 3x squared minus 3x plus 5. And then instead of a delta x, we're going to fill in a dx to our new notation. Let's try that one more time. So if I were to translate this to an integral notation instead of an infinite sum, I would have the integral from 0 to 1. Instead of the square root of 4 minus c sub k, I would just have square root of 4 minus x squared. And then instead of a delta x, I would just have a dx. Saying this and saying this mean the same thing. But because this notation is much easier to work with, we need to be able to translate this notation to this one so we can do problems in a more simplified way. Now what we're going to be doing today is learning how we can use antiderivatives to get these numbers exactly, these areas exactly, without having to actually add up infinity rectangles. It would be very impractical to try to add together infinity rectangles. It would literally be impossible to do. So what we have found is that we can use an antiderivative to get the same answer. Before we do antiderivatives, let's review some rules about derivatives. So if I asked you to take the derivative of each of these functions, the derivative of f of x equals x squared plus 3x plus 8 would just be 2x plus 3. The derivative of f of x equals x squared plus 3x minus 100 would be f prime of x equals 2x plus 3. Now you'll notice that the derivatives here are the same even though the original functions were not. And the reason for that is because when you have this constant term at the end, it disappears when you take the derivative. So even though there was a constant term in the original problem, the derivative doesn't have anything to represent that that constant was there. Now if I give you f of x equals sine of x plus 8, the derivative would be cosine of x. And if I give you f of x equals sine of x minus 10, the derivative would be cosine of x. Once again, the constant term at the end disappeared, so we couldn't have known that it was there if we didn't have the original function to look at. If we only had the derivative, we wouldn't have known that that was there. Now that's going to be really important because we have some rules about taking antiderivatives, and we're going to need to figure out a way to represent that unknown constant that we don't know is there or not. So what is an antiderivative? Well, an antiderivative is a term we use to describe the reverse process of taking a derivative. So for example, if your original function is x cubed plus 8, then the derivative is 3x squared. If your derivative is 3x squared, then the antiderivative would be x cubed, but then we always write a plus c. Now the reason we write a plus c is because remember this plus 8 that disappeared when we took the derivative? We can't tell what that was from the derivative itself. Just by looking here, we wouldn't have known there was a plus 8. So we put a plus c to represent an unknown constant. So what does this plus c mean? Well, if you look at the review examples or at the example we just did, you're going to notice that the constant term always disappeared when we took the derivative. This is because the derivative of a constant is always 0. What that means, though, is that we cannot determine the value of that constant just by looking at the derivative. So we write a plus c as a placeholder for this unknown constant value. So here are some rules. Now we did an investigation in class that hopefully allowed you to start thinking about some of these rules, and we're going to formally write down what you do with these rules now. We're going to start with the rule for constant functions. If your derivative is just a number, then the antiderivative, or the original, would have just been that number times x plus c. And the reason it would be that number times x is that when you take the derivative, if we look at our previous example, of a number times x, you just get a number. So if you just have a number, you get a number times x. For example, if your derivative is just the function f prime of x equals 8, then your original would have been 8x plus c. Now, if your derivative is a number times x to a power, so we're talking about polynomial functions now, kind of like what happened here with x squared. We need to undo the power rule. Now, the power rule says you multiply by the power and subtract the power by 1. So to undo that, we're going to add 1 to the power and divide by that number. So if your derivative is a number times x to a power, then your antiderivative would be x to a number that is 1 bigger. So instead of n, it would be n plus 1. And then instead of multiplying by that new power, the way that we do when we do a derivative, we would divide by that power. Don't forget that in this case, we also need to write a plus c. So let's look at an example. If your derivative is 4x squared, then your antiderivative, or in other words, the original, would be x to the third. So you should always start by increasing the power by 1. Then dividing by that new power. So 4 divided by 3, which is the new power, plus c. Last but not least for this initial row of rules is powers of -1. Now powers of -1 work a little bit differently than powers that are not a -1. And the reason is because you cannot use the power rule here. So you cannot use this one. Because if you have x to the -1, and you add 1 to that power, you would get x to the 0. And x to the 0 really just equals 1. So you would be saying that the antiderivative of x to the -1 is just 1, which is inaccurate. So in order to do the antiderivative of a power of a -1, so this is really the same thing as x to the -1, we need to remember that the only function whose derivative puts a variable in the denominator is natural log. So the antiderivative would be the natural log of the absolute value of x plus c. A couple important things to remember here. It needs to be natural log when it's a -1 power. There needs to be an absolute value. And the reason we need to have an absolute value is that natural logs cannot have inputs of negative numbers. So we need to force all of our numbers to be positive. And if we look at an example, if our derivative is 3 over x, then our antiderivative would be 3 times the natural log of the absolute value of x plus c. Now the rest of these rules are pretty straightforward. So personally, I think these 3 rules are the most difficult ones to sort of master at the beginning. Hopefully they make sense to you right now. Here are some rules for like trig functions, natural log functions, e functions, etc. So if we look at sine, if your derivative is sine, then the original, the antiderivative, would have been negative cosine of x plus c. If your derivative is cosine, then the antiderivative would have been sine of x plus c. If your derivative is secant squared, then your antiderivative would have been tangent of x plus c. If your derivative is secant times tangent, then your antiderivative would have been secant of x plus c. If your derivative is cosecant cotangent, then your antiderivative would have been negative cosecant of x plus c. And if your derivative is cosecant squared, your antiderivative would be negative cotangent of x squared. Plus c. Now, when we learned how to take derivatives, we said if you take the derivative of anything that starts with a c, you end up with a negative. In antiderivatives, if your answer starts with c, then you change the sign. So it's the opposite. Instead of the original starting with c, because we're going backwards, if the answer starts with c, we change the sign. So you'll notice that when we took the antiderivative of sine, we got cosine and we made it negative. When we took the antiderivative of cosecant cotangent, we got cosecant and we made it negative. Let's take a look at some exponential problems. So if your derivative is e to the x, then your antiderivative is just e to the x plus c. If your derivative is 1 over x, then your antiderivative is the natural log of absolute value of x plus c. If your derivative is 3 to the x, then your antiderivative is 3 to the x. But because when you take the derivative, you have to multiply by the natural log of 3, you have to divide by the natural log of 3 here, plus c. If your derivative is 1 over x times the natural log of 3, then that would have originally started at log base 3 of x plus c. If your derivative is 1 over the square root of 1 minus x squared, your antiderivative would have been inverse sine of x plus c. 1 over 1 plus x squared would have been inverse tangent of x plus c. 1 over the absolute value of x times the square root of x squared minus 1 would have been inverse secant of x plus c. Now if you make any of those negatives, you just get the other guy. So this guy's antiderivative would have been inverse cosine. This guy's antiderivative would have been cotangent, inverse cotangent. And this guy's antiderivative would have been inverse cosecant. So how does this work? Well, if I give you a derivative and I say figure out the antiderivative, the first thing you're going to do is you're going to go through one term at a time and see if you can do each term separately. So the antiderivative of 3e to the x would have been 3e to the x. The antiderivative of 5x to the 1/2, I would have taken my power, I would add 1, so 1/2 plus 1 would be 3/2, and then I would divide by 3/2. So I would have minus 5 and then divided by 3/2. The antiderivative of 1/2 secant squared of x would have been 1/2 tangent of x. And the antiderivative of negative 1 over 1 plus x squared would have been plus cotangent inverse of x. And at the end of that whole thing, I would put a plus c. Now what I'm going to do is just simplify a little bit. So 3e to the x would just be 3e to the x. 5 divided by 3/2 is 10/3 x to the 3/2 plus 1/2 tangent of x plus cotangent of the inverse of x plus c. And then here's the best part. We can check ourselves. So let's take this function. And let's take the derivative and see if we get back to what our original problem said. If I think back to what I learned for an entire semester, the derivative of v to the x is just e to the x. If I drop the 3/2, the 3's cancel. 10 divided by 2 is 5x to the, subtract 1, I get 1/2. Plus 1/2, the derivative of tangent is secant squared. And the derivative of cotangent is negative 1 over 1 plus x squared, which is the same thing I started with here. So I know that I got my antiderivative right. I would strongly encourage all of us to get into the habit of checking ourselves by taking the derivative before we move on to the rest of the problem. All right, that's the end of our video. Thank you guys so much for watching. I really appreciate it, and I will see you tomorrow for some practice. Here we go.